Hello, I'm Chen Liang from Zhejiang University, and today I'm gonna talking about visual abductive reasoning, and also called VAR. So, what is abductive reasoning? By definition, it is the inference to the most likely explanation from an incomplete set of observations. And in this work, we focus on this ability in visual situations. And for illustrative examples, so if you see that the road is wet, you may infer that it rained earlier. In the morning, you find that your sister leaves home hurriedly, then you may conclude that she will be late for class. And if you see that a boy threw the frisbee out and his dog is running after it, and later you find that the frisbee is in the boy's hand, you can imagine that the dog just called the frisbee back. What we have done is to infer the most probable explanation to what we observed in vision, and that is the visual abductive reasoning. In this work, we are trying to examine this ability of machine intelligence in form of natural language expressions. For example, so given some logically related events, the AI system is asked to describe these premise events. And more importantly, it is also needed to infer and write down the explanations. Accordingly, VAR dataset is inbuilt. We select logically related events by human experts for further annotation. And the first step is to annotate the type of each event and derive legal examples. And then the next step, we annotate all the events with abductive reasoning-oriented descriptions, and that means some detailed descriptions like the color of the man's clothes is ignored. As summary, from a large-scale number of YouTube lifestyle vlogs, TV shows, and movie videos, we clean and select about 4,000 videos in total for further annotation, and result in the first large-scale dataset that is designed for VAR. It contains diverse cause-effect relations and abduction cases and covers over 8,000 examples in total. With this high-quality testbed, we are ready to study, examine the VAR ability in machine intelligence, and serves as a proper baseline for VAR with proposed reasoner. It follows an encoder-decoder transformer architecture. As an overview, for encoder, it takes video sequences and encodes the visual features. And then the decoder takes these features and decodes each description autoregressively. And specifically in decoder, a relative position embedding is adopted regarding the relative ordering of the plausible chains of cause and effect. And the embedding is also conditioned on the specific content of current clip. And for example, so when we see people laughing, we tend to look back only a short time into the past to figure out the reason. And for the decoder, we stack several transform blocks. Each takes the output from the last block and tries to refine them conditioned on the predictive confidence of each event. And here we define the average of the predictive score of each word as the confidence. And here 0 stands for the output of the first block, and this allows reasoners to make full use of both visual and linguistic context and improves the hypothesis in a step-by-step manner. And finally, we benchmark the model performance on VAR and found that reasoner surpasses many famous models while still being far from human performance. When come to the user study, the same conclusion is still drawn, and remaining large high room for AI systems in VAR is still observed, that is expected to encourage exciting avenues in the future. And we further test reasoner on dense video captioning task, which can be seen as a boundary case of VAR that all events are observed to the system. And on activity net captioning validation set, reasoner outperforms state-of-the-art models. This also proves the strong reasoning ability of reasoner and emphasizes the value of VAR task in promoting innovations of powerful video language models. And that is all about VAR. All our data and code are available online on GitHub, and thanks for your attention.